Alright, what's up guys? This is Physics 2, Lab 6, Magnetic Molasses. Alright, so the purpose of the lab is to compare the experimental time it takes for the bar magnet to fall through a tube of aluminum foil and the simulated time calculated by the computational model. Systems, the bar magnet, the surroundings is the role of the aluminum foil, earth, and everything else. We're making air resistance negligible, and the induced magnetic field is what affects the magnetic motion. The foil is uniformly distributed, and there's all the measurements for it. Here we go. Fundamental principles. So we need Faraday's law to calculate the flux. We need the magnetic field of a dipole to see how strong the magnet is. We need the position velocity update formulas just to see how fast are things falling. We need the magnetic force on a wire loop. We need EMF, and we need force of gravity, which is F equals mg. Next, we have the experimental procedure. To do that, we start recording, drop the bar magnet through, repeat 5 times to average it out, and then we watch the video for the timestamps to calculate the average time. You can see we did it here. And drops the magnet down the tube. You see it comes out. So there we use the frames for that one to calculate the time. Here's our computational model. You can see the geometry of the tubes put in first. Then the, that's just given stuff. Then the properties of the magnet, which we calculated for. This is what we calculated for in like lab 2 or 3, I think. Yeah, and this has the biggest effect on the whole thing. So if the bar magnet wasn't quite the same, it didn't work the same. So kind of manipulated this to be a little closer to the true value. The observations. So the intensity of the coloring on the tube indicates the magnet of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. So applying Lenz's law, the red color must be counterclockwise and the blue as clockwise, as the combination would oppose the magnet's motion. That's just some simple stuff right there. What happens to the dynamic system when you flip the magnet around? Well, the system's not changed, but the magnet's still allowed to slow down, and the currents are opposite. And how does the total time of the tube of the real-world system compare to the computational system? Well, so the computational system doesn't account for some outside forces like air resistance and friction, like, for example, the magnet tumbling down as well as being slowed by the Lorentz force. But yeah, you can see here it's just a smooth graph that's not affected by anything else. So the forces are unbalanced for the first 0.1 seconds, you can see, and then they're balanced for the next 1.3 seconds as it's pretty much it would be tumbling through. And then it speeds up again after it leaves the tube. So source of error, other magnetic fields present. There are tons of magnetic fields all around, so it could definitely mess it up, and even the Earth's magnetic field can mess with it a little bit. There's errors when measuring visually. Obviously, the frame rate, it could come within some hundredth of a second and not be 100% correct. The friction with the walls of the aluminum roll as it rolls down. The air resistance is also not accounted for, and also non-uniform distribution of the aluminum foil, so it could have different forces. So the what ifs. What if the resistivity of the conductor were reduced as close as possible to 0? Well, this would make a very small resistance and a very large current. So this would increase the magnetic force and make the magnet fall very slowly through the tube. The less resistance you have, the higher the current can go. So what if holes or slots were cut in the tube? Holes or slots would just disrupt the induced current and decrease it. It would be like increasing resistance there. It's just taking longer for less field can be created from that. Well, anyways, the conclusion was that the computational model is correct, minus the things that were disregarded. Anyways, thanks for watching.